All right, we're going on to question 5. It is about a motorbike, and I suspect that we've got something to do with forces and things here as well, maybe even some momentum. The track for a motorbike consists of a straight horizontal section that is 800 meters long. So here's the motorcyclist, and he's traveling along that straight horizontal track. A participant, such as the one in the picture in the previous slide, rides at a certain average speed, so we know that he's got a certain average speed, and he completes, and it's an average speed, so we're just going to assume that that remains constant, okay? It might vary just a little bit, but there is an average speed that we're going to work with because it's easier that way. 800 meters course, and he takes 75 seconds. This is not a superbike racer by any manner of speaking. So to maintain this speed, a constant driving force of 240 newtons acts on the motorbike. All right, we go back. We see that there is a constant from the engine here and making the wheels turn. There is a constant force acting in that direction, 240 newtons. We are told that it's a straight road. Well, is there going to be some friction? I'd kind of suspected. Let's see if we're going to get that thrown at us. We know what its distance, we know time. Calculate the average power developed by the motorbike for this motion. Okay, what is power? Power is equal to work over time. Power is the rate at which work is done. Now, do we know the time that he has taken? Yes, we do. Do we know how much work? Yes, so we ask the question, yes, we do know. Do we know how much work he's done? Well, I know that work is equal to the driving force or the net force multiplied by the distance in the direction of the force. Now, everything here is in the same direction. There's a force of 240 newtons, and he is pushing it over 800 meters in a time of 75 seconds. You know, I've got everything that I need to work this out. So power is equal to the net force times delta x over delta t. And just by the way, delta x there. Getting excited because what I wanted to show you is, you see, that's something else that you get in your data sheet. Delta x over delta t is equal to the velocity, the rate of change of displacement, or the rate of displacement rather there. So that's the velocity. So in other words, power is the net force times the velocity that the body is moving. So we can do it in any one of those ways. If we knew the velocity, then we could work it out. So this is 240 times 800 over 75. And, well, 25 will go in there 3 times. 25 will go in there 32 times, which is 8 times 4. And 3 will go in there 80 times. And 80 times 32, we're going to get an answer of 2560 units. This is not, in fact, you know what, I really should write that W as a little w so we don't confuse it with the units of power, which is watts. And there is your answer. And if you wanted to, you could say, it would be quite correct to say, to divide this by 1,000 and say kilowatts. Because when you talk about engine powers, generally kilowatts will be used. So 2,56 kilowatts or 2,560 watts, both is correct, either is correct. And this one just tells you that you know something about motors and the order of magnitude of the powers that are involved. Okay, so there we go. We could have worked out velocity first and then just multiplied by delta t, but that was an extra step. I don't think it was necessary.